Hello, this is the first video for section 6.7, which is all about physical applications. So, how can we use integrals in the realm of physics? So, throughout these videos, some of these formulas, if you've done a calculus-based physics, you may see before, but we are focusing in on how can we get integrals to get us to some of these formulas. So first, in this video, we are talking about density and mass. So the definition, density is the concentration of mass in an object. Usually density indicates mass per volume. So mass would be density times volume when density is uniform across the object. But if the density varies, we're going to need calculus. And getting a 2 or 3-dimensional objects, that is going to get complicated and can be saved for later calculus classes. But for 1-dimensional objects, we can talk about linear density. So suppose we have a very thin 1-dimensional object, like a very skinny wire, stretching from A to B. And we want to find the mass of this object given that the object's linear density, rho, varies along its length. So using the same idea from previous classes and using the fact that mass equals density times volume, if I slice up my interval into small little pieces, and I say I want to look at this small little interval from xi minus 1 to xi. Then, to find the mass of this tiny little interval, that will be equal to some density in this interval. Let's say the endpoint on the xi side. And that density will represent that whole length of thin bar. And so we have the density and then the volume of that thin bar. Well, it's only one dimension, so the volume is just the length of that thin bar, which is that small little interval delta x, set up very similarly to our typical standard integral setups, where if that is the mass being represented for one small little bit of this bar, then if I add up all my little pieces of bar, all those masses, and then take the limit, as n goes to infinity, this will be the mass of the whole bar. But this limit sum delta x is the integral. So to find the mass of a 1-dimensional object, it is the integral from our positions of A to B of our linear density function, dx. So we can use that integral to find the mass of a bar. So as an example, suppose we have a thin 2-meter bar represented by the interval 0 to x, so 0 to pi. We want to find the mass of it if the density, its linear density, is given by rho of x equals 2 plus cosine x. Using the formula, using the integral, mass equals the integral from 0 to pi. does not matter that it's 2 meters long. It's being represented by a bar where the beginning of the bar is 0 and the end of the bar is pi. So our integral is 0 to pi of our density function 2 plus cosine x Now we can integrate this. The integral is 2x plus sine x being evaluated from 0 to pi. Plugging in our upper bound, we'd have 2 pi plus sine pi minus 2 times 0 plus sine of 0. Sine of pi is 0. 2 times 0 is 0, and sine of 0 is 0. So this integral is 2 pi. And because we're in physical applications, we always need to make sure we have our units. So going back to make a note on units, we are finding a mass. And mass is going to be measured in kilograms or whatever we're doing, because we're having a density, which is mass per volume, multiplied by the volume. The volume part cancels and we're left with kilograms. In the next videos, we'll take a look at using integrals to find work and some specific applications of that.